Okay, guys, I'm back. Okay, so I have searched two videos for you in order to explain the submerged arc welding and shield metal arc welding. Okay, so these two welding procedures use the electrodes. Okay, so so this video will more elaborate. The first video I'm going to show you is about the submerged arc welding. Okay, so please pay attention. Okay. Let me check where is the sound. Why the sound is very low. Okay. So this is basically a submerged arc welding. Okay. Like the arc is submerged under this flux. Okay. And the arc. So, okay. And instead of a electrode, a stick electrode, a wire electrode is being used. Okay. Just see this video. I don't know what is what is wrong with its sound. So you can see the weld is going on under and they are submerged. Okay, so basically this is a shop technique. Okay, so you do welding with this technique at the shop. Okay. How much is left? Okay, now the things will get clear here from here. Okay. The next video is about that shield metal arc welding.
Shielded metal arc welding. Shielded metal arc welding is also referred to as stick welding or manual metal arc welding, in short, MMAW, in which an arc is struck between the flux-coated consumable electrode and the base metal to start the welding process. It is the most common type of welding process seen in any job shop industry. Working principle. In this process, the heat required to melt the consumable electrode and form a bond with the base metal is produced by an electric arc struck between the electrode and the workpiece. The shielding for the weld pool is provided by the flux, some of which is deposited on the layer of the weld in the form of slag, which is removed upon cooling. The choice of electrode depends upon the base metal composition. If you are new to ADTW Learn, click on the subscribe button and turn on all notifications so that you never miss an update. Equipment, or components of shielded metal arc welding. Power supply. Transformer. Most commonly, welding transformer, a DC rectifier, or a DC generator is used. Electrode holder. Electrode. Ground clamps. Working. First, the power adjustments are made on the transformer. The welding can be carried out by either using direct current electrode positive, DCEP, or direct current electrode negative, DCEN, connection. DCEN. In DCEN, the electrode is connected to the negative terminal, and the workpiece is connected to the positive terminal. The electrons thus travel from the negative terminal to the positive terminal. That is, from the electrode to the workpiece. Since there is a sufficient potential difference between the electrode and the workpiece, therefore the electrons from the electrode accelerate and strike the workpiece surface at a very high velocity. Upon striking, the kinetic energy of the electrons is converted into heat, or thermal energy, thus an immense amount of heat is generated at the workpiece surface. About 66% of the arc heat is generated on the surface of the workpiece, and the rest of the heat is generated at the electrode surface. This melts the base metal quickly, thus resulting in deeper penetration. However, the deposition rate of the filler metal reduces due to less heat generation at the electrode surface. DC. In this polarity configuration, the electrode is connected to the positive terminal, and the workpiece is connected to the negative terminal. And hence the flow of electrons is from the workpiece to the electrode. A major amount of arc heat is generated at the surface of the electrode, and less heat is generated at the workpiece surface, thus resulting in a higher filler deposition rate and insufficient fusion between the workpiece and filler metal. However, when the electrons flow from the workpiece, the dirt and oxide layer is disrupted, also known as arc leaning action, thus helping in producing a quality weld bead. After setting the necessary current and voltage parameter, an arc is struck by slightly touching the workpiece with the electrode and carrying forward or backward. Once the arc is struck, the heat generated melts the electrode and base metal, and the filler metal gets deposited on the base metal. The electrode should be held at a lower angle to the workpiece to initiate an arc and to carry on the welding process, but if the electrode is held perpendicular to the workpiece, then it is likely that the tip of the electrode may stick to the workpiece and fuse, causing it to heat up rapidly. The flux then converted into a shielding gas surrounding the weld pool, protecting it from oxygen and other atmospheric contaminations. Some of the flux gets settled on the weld puddle in the form of the slag. Once the welding is completed, and the weld bead is cooled down, the slag is chipped off using the chipping hammer, and cleaned using a wire brush. Shielded metal arc welding can be used to weld in all positions. That is, flat, horizontal, vertical, and overhead. Advantages. The initial cost is low. The welding equipment is simple and portable. Flexibility of the process in using a wide variety of electrodes. The electrode is flux coated, which provides shielding, hence no need for heavy gas cylinders of shielding gases. An efficient and low-cost way of joining metals, and good for welding in tight spaces. Disadvantages. A highly skilled person is required to produce a good quality weld. Defects are hard to detect in the weld. The process is manual and hence high labor cost. Fumes and gases produced by the flux are hazardous. Application. This process finds its application in structural welding, job shop, shipbuilding, field repair, marine, aerospace, and nuclear. Hope you have understood shielded metal arc welding process. If you like this video, click on the like button and want to learn from more such videos.
Okay. We will come back to our lecture now. So I hope these videos were useful in explaining the submerged arc welding and shielded metal arc welding. Okay. Okay, let me. Okay. So we will just remove them and Yes. Yes. Okay. Okay, now we will talk about the important consideration in welding process. Okay, like it's a the first important consideration is that the largest type of fillet weld, as we discussed, that there are different type of welds. We have groove welds, we have plug welds, we have slot welds. But for our concern, we will be sticking to the fillet welds. Okay, so fillet welds, like most fillet welds are those which can be made most efficient. Like this welding process, or this welding or fillet welds cannot be achieved in a single pass. Okay, there are multiple passes of deposition of the base electrode metal. Okay, which has to be carried out in passes, or in in not as in single pass you can complete the weld. Okay, but the most efficient fillet welds are those welds which can be made in a single pass. Okay, so so in this video you will see that when the pass out cools, there are impurities which penetrates, or which is at the surface, which are being, that is called slag, and this slag is removed after one pass is completed. Please remember that in order to the maximum size of the weld, fillet weld, which can be achieved in a single pass, is 5 by 16, and this is by American Welding Society guidelines. Okay, so now the other thing is that the largest, like there is a constraint on the size of the weld based on the deposition process. Okay, like it says that when you are doing welding in a horizontal or overhead position, the size should not exceed by 5 by 16 inches. Okay, and if you are doing welding in a flat position, the size of the weld should not exceed 3 by 8 inches. And if you are doing welding in a vertical position, the maximum size of the weld should be 1 by 2 inches. And please remember that whenever we are doing the design of a welded connection, okay, welded connection, so how we can calculate the maximum size of the weld? So we can do that using this simple formulation. We have to determine the thickness of the members. Okay, you have to subtract from the thickness a size of the 1 by 16. So this will give you the maximum size of the weld. Okay, this will give you that thickness of the weld. Okay, please remember that you have to perform this operation in each and every problem where concerning fillet welded connection. Okay, so these are the some of the important considerations in the fillet welding. Okay, and as I told you that if the fillet weld is too small compared to the thickness of the material, for example, you have two plates and the thickness of these plates is very high. It is larger, very larger than the size of the weld. Okay, so what happens that this, if the thickness is higher than the welding size, so what will happen that there will be there will be tensile stresses that will be introduced in this fillet weld. Okay, and this is due to the uh, cooling. Okay, non-uniform cooling of the weld. Okay, this phenomena is explained here that the amount of heat required to deposit a small weld is not sufficient to produce appreciable expansion of the thick material, and as the hotter weld contracts during the cooling, it is restrained by being attached to the cooler material, and the tensile stresses produce which may cause crack of the weld. Okay, so this is about, like, you have to be very careful, like, you in selecting the minimum size of the weld. Okay, and this is like you have the a table this, which is given by this American Welding Society. The minimum sizes are given. Okay, based on the thickness, based on the thickness thicknesses of the steel members. minimum sizes are recommended. Minimum size is of fillet welds are recommended. Okay. Okay. Now we will have some nomenclature of the fillet weld in this slide. Like as I told you that fillet welds can be used for those members which are those surfaces which are at right angle. Okay. So fillet weld consists of a right angle triangle. Okay. And this angle in a fillet is about 45 degree. Okay. This is 45 degree. And this is a right angle triangle. Okay. Now this point in fillet weld we call it root. Okay. And this point, this line we call it throat. Okay. This is throat. And this portion, these portions of the triangle of the fillet welds, we call it legs. Okay. These are the legs. Okay. So we have equal leg fillet. Okay. For equal leg fillet, the throat of the fillet weld triangle is about 0.707 times the length of the fillet. Okay. What it is saying is that, for example, you have this fillet. Okay. Oh, this is the throat, and this is saying, say this is S. Okay. For equal leg fillet weld, this is S. This throat is equal to 0.707 times the leg of the fillet weld. Okay. So you can use the trigonometry. You can derive this. Okay. By and the throat by how wide the throat is 0.707 times the leg size. You can simply use the trigonometric rules or trigonometric knowledge to derive that this will come out to be 0.707 times the size of the legs. Okay. So this is explained here. Okay. And throat, why we are interested in throats? Throats are because the stresses in fillet welds are resisted at throat. Okay. So throat is very important. Okay. Stresses and in case of fillet weld, so we assume that they are vulnerable in shear. Okay. Of course they will be subjected to tension, they will be subjected to compression, but we in fillet welds it is recommended that the fillet weld fail in shear. Okay. Now there are some symbology concerning these fillet welds and groove welds, like they might appear on the drawing. Okay. So for example, if you have this type of symbol, okay, 5/16 is representing the leg. This is an equal leg fillet. If you see a triangle and it is on the upper side and it is pointing toward the joint, it means that this side is to be welded. Okay. Similarly, if you have double triangle, so it means both sides should be welded. Okay. If you have this type of symbology, so you will have this type of fillet. This should be the required position of the fillet in the field. If you have this type of symbology, like 1/4 is the size of the leg again, and 6 is the length. Okay. So it means that if you have this is over this arrow, it means that weld should be deposited to this side of the joint. Okay. Similarly, if you have this one, this symbology, okay, 2, 4. Okay, this is 2, this is 4. Okay. So if you have this type of unequal leg triangle, okay, so this means that this side should be welded. Okay. One side should be 1/4, the second side both leg size are mentioned. Okay, if there have been equal leg triangle, only one side has should be is mentioned. Okay, for equal leg only one leg size is mentioned. Okay, for unequal both legs are mentioned. Okay, similarly how the groove welds are represented on drawing. Okay, like this. Okay, if you have this one, so you have to make a groove in this shape. Similarly, if you have this one 40 degrees, so on. Okay, okay, okay. Now this is about the groove welds. Okay, groove welds may be stressed in tension, compression, shear, or combination of tension, compression, and shear, depending upon the direction and the position of the load relative to the weld. If you have this type of position, like you have this groove weld and the load is acting transverse to the axis of this weld, so how you can compute the stresses that will be induced in this weld. Okay, and induced in the weld. Okay, so the magnitude, how you can compute the magnitude using this formulation. This direction. Okay, so I think this formulation belongs to this one. Okay, and if the load is acting in this direction, okay, it is along the axis of the weld, so the load will be the stresses which will be produced at the throat in the fillet will be this much. Okay, half, this will become half. Okay, TL, these are the stresses. Okay, TL is the length, L is, this is the effective area, this is the effective area. Okay, F is the stresses. Okay, L and TE is the effective area. So we know that load is equal to stresses times area or effective area. Okay, so load, you can say load is represented by P, stresses is represented by F, area is like effective area. Okay, effective area means here that if this is a throat here, this is a fillet weld. Okay, for example, and this is the throat length. This throat length into the length of the fillet weld. This is the length of the weld. Okay, for example. Okay, now this length should be multiplied by this throat length in order to get the effective area. Okay, but in case of design of weld, we mostly take the length of the weld as 1 inches. Okay, so this is equal to the throat length. Okay, if you multiply one here, so this is how you can compute the shear stresses. Okay, shear stresses in fillet welds. Okay, if the half of the load is here, so you have to replace this total P by 2. Okay, so this is how, like the stresses, this is just I wanted to explain the formulation. Okay. Okay, the test have shown that if the load is applied on the axis. Okay, okay, or if it is applied perpendicular to the fillet weld, so fillet welds are more effective when the load is applied in the direction normal to the axis of the welds. Okay, so they are much stronger. Fillet welds are stronger when subjected loads acting in the transverse direction. Transverse direction of the axis of the load. Okay? They are much more stronger when the load is in this direction, and they are weaker when the load is acting along the axis of the weld. Okay. Now, stress is the load sharing of fillet weld depends upon, like, you can provide the fillet welds, like, let me explain it here. Okay. For example, you have two plates here. Just give me a moment. Okay. So you want to weld them together. Okay. I'm drawing two plates. Okay. This is a plane. Okay. You can weld it here. You can provide a weld here. Okay. I'm drawing it here. Okay. And load is acting in this direction. Okay. So whenever we talk about design of welded connections, I'm sorry, design of welds. So it means length of the weld. Okay. Like the applied load is resisted by the length of the weld. Okay. If the load is still, or demand is very high, what we have to do is that we can provide a weld on this side as well. Okay. Okay, obviously it should be like this load for this case of symmetrical connection. So first the length should be provided up to here and to the both sides of this plate. Okay, if the load extends to the end of this plate, so we extend it here. Okay, here. Okay, this way. Okay, so this we call end returns. End returns. Okay. Okay, the thing that this slide is demonstrating is that applied load is proportional to the length of the weld and area of the weld. Okay, area the weld. Okay. If the fillet, you can increase, either you can increase the length or either you can increase the size of the fillet. Okay, you can go for a larger leg weld. Okay, if the demand on your structure is high. Okay, is that clear to all of you?
Yes,
Yes,
sir.
sir.
मैं तो लग रहा है अपने साथ ही लगा हूं, लेकिन चलें ठीक है, आप लोगों को समझ आ रही है तो अच्छी बात है। देखें, आपने क्या करना है, अगर डिमांड बहुत ज्यादा है तो आपने लेंथ इंक्रीज करनी है या आपने इसका एरिया इंक्रीज करना है। ठीक है, अच्छा, the second is that if the load is applied in this direction, I will just explain it. So if this is the situation, so then you will have a stress concentration here. Stress concentration. Okay, concentration. I'm sorry if the spelling is wrong. So, but what you do once you extend it like this, so this will become this case. There will be no stress concentration and load will be smoothly transferred. Okay, load will be smoothly transferred. Okay, Okay, you can go through this slide. Any abrupt discontinuity or change in the section of such as notch or sharp reentrant corner interrupts the transmission. Okay, so but you elongate that. Okay, so then you have more smooth stress transfer. Okay, you can read out this slide. Okay, this is stating the same thing as I have explained to you people. Okay, now as I told you that our concern or what we are going to discuss is S SM. Yes, this is SMAW or SAW. Okay, field welds, we go for this one. Okay, so these two welding processes use make of electrodes. Okay, so electrodes, okay, they make use of electrodes. And how electrodes are designated? They are designated with some sign EXXXX. Okay, now, welding electrodes are classified, or these electrodes are classified on the basis of mechanical properties of the weld metal, welding position, type of coating, type of current required. And mostly they are designated like EXXX. So XX means like E, like it can be E70, 1, 8. Okay, and I have X is just to designate the number. The first two number on the electrode is the tensile strength. Okay, okay, this is the tensile strength of the metal, welding metal. Okay, the next represents the welding position. If it is 1, it means all positions. Okay, you can use this weld for in all positions. Okay, so we can go back to the next slide, second slide. Okay, the first two numbers, for example, the first two numbers is, or three numbers designate the 2 or 3. They designate the tensile strength of the electrode. Okay, next, position in which electrode can be used. 1 means it can be used in all position. The next one. Okay, this is the next one. And these 3 or 2, mostly 2. Okay, they represent the tensile strength of the electrode. Okay, the last number denotes the type of covering of flux or type of current, AC, DC. Okay, so there is an example like E7018 means that this electrode has a 70 ksi strength. 1 means it can be used in all welding positions. Okay, 8 means it is an iron powder. Okay, okay, where it is mentioned iron powder, low hydrogen, just for, but our concern is for the these three digits. Okay, tensile strength and position in which it can be used for welding. So there are some specification. Okay, like these specification about the mechanical properties of the flux coated coating material. Okay, so I have taken it from our teacher, Professor Akhtar Naeem Sansam. It is mentioned in the Gellert book, but the book which we are following does not require these requirements, but you can go through it. Okay, if you, there is some discussion like ASHTO, area. What is area replaced with now? Area का भी नया नाम क्या है? Arium. Okay, so this is an old, like this is important. Okay, but as I told you that there is a minimum size requirement on the fillet weld. Okay, if the thickness, based on the thickness of the plates which you want to connect. Okay, for example, if the thickness of the plate is up to 1/4 inches, so you will use fillet weld which has a leg size of 1/8. Okay, if the thickness is in between 1/4 to 1/2, you will use this size of the weld. Okay, so this is like you have this requirement. Okay, minimum size of fillet welds. Okay, based on the thickness of the steel members. Okay, so these are the mechanical properties. Like you can see here, if you are using shield metal arc welding, so they will be designated like this. And mostly in our problems, you will see we will be using shield metal arc welding. Okay, if you are using submerged arc welding, so the electrodes will be designated this like this. Okay, gas metal arc. Okay, so mostly this is of our concern. Okay, the mechanical properties are mentioned. Okay, you can find them in the Gillard book as well. Okay, for example, this is the filler material. Okay, so in this code requirement, this is our concern is the fillet welds. So in fillet welds, we will use a phi which is 0.75, and the tensile strength of the electrode we will use as 0.60 EXX. Okay, we are not discussing plug or slot welds, but you can go through this information if you are interested. Okay, again, now when we go for the fillet weld design, okay, so there are three limit states, so there are three requirements you have to check. Okay, the first is the shear strength of the welded material. Okay, and this you can check with this simple formulation. Okay, over here you see that 0.70. I'm sorry. Okay, this 0.70, just give me a moment. Okay, I will remove this one from here now. Okay, yes. Now you remember that phi from in AST or LRFD from the specification we have seen for fillet weld, phi value is 0.75. Okay, and when we discuss the effective area, okay, the stresses in the, like we discussed that effective area for fillet weld is equal to 0.707 times the leg of the fillet weld. This is basically here, this one. And this is the stresses, okay? Like based on the, like for example, if the electrode tensile strength is 70 KSI, you have to reduce it to 0.6. Okay, basically you have to check for the shear strength of the weld, you have to check for the shear yielding of the base material over which the weld is deposited, you have to check the shear fracture, okay, using this formulation. So we will go through a problem and you will see how we can use this. Okay, this is why I'm showing this. Okay, now this is about this one, like how you can calculate the nominal resistance or shear resistance of fillet weld. Okay, if the fillet weld width is W, length is L, okay, we have to multiply stresses with area. This area is, we already know, and this is stresses. Okay, okay, now this is the equation. Okay, now this equation, like this equation, please remember this equation. Okay, this is for the, to evaluate the shear strength of the connection. Okay, this is Rn is equal to 0.707 times W into zero point 0.6 into this one. Okay, this is for the case that when the applied load, okay, if this is a fillet or like this, if the applied load is parallel to the axis of the weld, okay, so you will use this formulation. Okay, parallel to the axis of the weld, then you will modify your equation and then you will add this term 1 plus 0.5, yes, this one. Okay, once the applied load is not parallel to the axis of the weld, what you have to do is that you will use this formulation into 0.6 EXX multiplied by 1 plus 0.5 sine power 1.5, okay, into theta, yes. So if the axis is parallel, you will go for this equation. If the axis is not parallel, load is not parallel to the axis of the weld, then you will go for this formulation. Okay. So this is what it is showing, that when the axis is not parallel, so you can use this equation. Okay. Now this is an example. Okay. A very simple example. Okay. So what it asks you that a plate used as a tension member in a connected gusset plate as shown in the figure. Okay, this is shown. The weld size is 3 by 16 inches and it is made of fillet welds. Okay. What I would like you people to do is that note down the thicknesses. Okay. Note down the thicknesses of these plates. Okay. One is 3 by 8 inches and one is 1 by 4 inches. Okay. So you have to select the minimum size of the weld. How we can do it? कैसे करेंगे हम?
Thickness minus 1 by 16.
ये भी हो सकता है. That will give you the maximum size of the weld. Okay. That is maximum size of the weld. And how to check the minimum size of the weld? So for that, the 1 by 4 means, okay, over here, 1 by 4 means point, wait is, yes, 0.25. And 3 by 8 means 0.375, okay. So we will go back to that table if you remember this table. If the thickness is up to 1 by 4, then you have to use this one. If the thickness is between this one, so you will go for this fillet weld, 3 by 16. Okay. So the fillet weld here is about 3 by 6 inch weld made with an electrode of 70xx. 70 is the tensile strength of that electrode. The connected parts are A36 steel. Okay, this is very important. Assume that tensile strength of the member is adequate. Okay, we do not have to perform, we do not have to check the tensile strength of the tensile member. Okay, so what you have to do, you have to use these three equations. The first equation is, first we will check the nominal strength of the shear strength of the weld, and for that we have to use this simple equation. The load is parallel to the axis of the weld. Okay, this load will be this is 4 inches and this is 4 inches. This load will be equally resisted by these two welds. Okay, so what we are going to do, we are going to use this equation. Okay, you just plug in the value. We have the leg size of the weld. This is 7.707 times 3 by 16 into 0.6 of 70, because the electrode is E70. So this comes out to be, the length is not mentioned here, length is 1. Okay, so you will get the nominal resistance of this fillet weld as 5.56 kips per inch. Okay, this is the one of the limit state, or one of the check we have to perform for fillet weld design. Okay, the second is we have to check the shear strength, or design shear strength of the, sorry, you have, once you multiply this value with 0.75, so you will calculate the design strength of the weld. Okay, then you have to check the base metal shear yielding and rupture, and since this material is made of A36 steel, for A36 steel Fy is 60 ksi, Fu is 58 ksi. So you use the second equation and you plug in the values here. Okay, this is 0.6 FYT, 1.63. Okay, this he has checked for the gusset plate. Okay, this is the least thickness, has the least thickness. So this is the controlling one. Okay, just give me a moment. Just give me a moment. Assalamu alaikum, sir. जी सर, अवेलेबल सर. न सर, मा सर वो निश्चित सर दाशी ना सर, लेकिन how they التبو الشات سبا فيسكي بچا سري جانا براوالو سر بس سر زه کلاس کې هم بس دا کلاس ختميږي نو ورځم سر ٹھیک شو sorry for the interruption. Okay, three values. Okay, once you calculate these three values, you have to see which one of them is the least value. Okay, the least value is the controlling value. Okay, once you have the least value, okay, let me see. Okay, just okay, this one. Yes. Now let me turn on my pen. Okay. So we use the three equations. Okay, the first equation is this one. The second equation concerning the steel members is this is shear rupture and shear yielding. So we check that. The first is this strength, weld strength is 4.176. Okay, 176 kips per inch. And the second is, and the third is 6.525. Okay, so the least value will be the controlling value. Okay, the shear strength of the weld is controlling. Okay, not the shear yielding or shear rupture. So what you are going to do, that you have a length of 4 inches to the both side of this member. So what you are going to do is that what is required, let me check that. Use the weld or melding this, the connected parts. Determine the available strength. Okay, so we have to determine the strength of the weld. So how we can do it? We just have to multiply this 8 inches, because this 8 inches is 4 plus 4. 8 multiplied with the 4.176. So this will be the strength of the member weld. Okay, this comes out to be 33.4 kips. Similarly, this was based on LRFD approach. For ASD approach, what we have to do, we have to divide it by a factor of safeties. Okay, so different factor of safeties are used for different limit state. Factor of safety for the shear strength is 2. This is 1.5, and for rupture this is again 2. So you have to check this Rn is here, so you just divide it. Now we have to check the shear yield. So this is 3.6. This is still controlling. This is shear rupture. This is 4.35. So what you have to do is that you have to multiply this value with the length of the weld. Okay, what is the total length of the weld? Total length of the weld is about 8 inches. 4 plus 4. Okay, if it had some end return, so we would have added that for end returns. Okay, like this. Yes, फिर हम उनको भी ऐड कर लेते हैं. So you had to have 2 inches or 4 inches, whatever. So what you do, you have to multiply it with this, the least value, which is controlling value, and you will get the strength of this welded connection. Any questions?
No, sir.
Asan, is it easy or you don't like to ask questions?
Easy, sir. Easy.
Well, when you go to the doctor, so you get the tablets, you don't ask him what is this and what is this. You just take it and you get well. So when we are doing steel design, so you just have to follow the equations which are recommended by the code. Okay, so there is nothing much I can do about it. Okay, you just have to remember the factor of safety, the few values, and all other stuff. Okay. So there is a second question. Okay, the second question is about this is a continuation of the first question. And in this question, it says that if the connection includes both 4-inch long welds and additional 4-inch transverse weld, okay? It is saying that in the last, yes, over here. So this was the member like this. It was welded here, fillet welded here, yes. And it was 4 inches. Okay, this was from example 7.12, okay. But in 7.13, it also says that there is a end return of 4 inches. So the total length will become 4 plus 4 plus 4. This is 4, this is 4, and this is also 4. So instead of multiplying with the 8 inches, you have to multiply it with the 12 inches. So what happened that the length has increased, okay? The length of the weld is enhanced. So the strength of the connection will also increase. So from previous examples, we know the design shear strength was controlling. It was about 7.146. And from example, the base metal was this one. So this was controlling. So how you can calculate the strength, you have, instead of multiplying with the 8, now you have to multiply it with the 12. So this will be the design strength, okay? Now what it says that whenever you want to make a check on the, what is it saying? I'm also lost. Okay, if you have to check the welded strength of the connection, so you have to do it in this way. You have to multiply the longitudinal weld, okay, with 0.8 factor, okay, and the transverse weld you have to multiply it with 1.5. So according to AISC, okay, so you have to do, whenever you want to check the strength of the weld, when it includes the transverse weld as well, so you have to do this 0.8 times the longitudinal length and plus 1.5 times the transverse weld, okay, transverse length, I'm sorry. So this has been done here. So this is the strength, okay. The larger length controls, okay. Which one is the larger one? Okay. The larger value control. So this is controlling, okay. This is not controlling. So how to do it in AST? You know that you have to divide it by this factor of safety, and this factor of safety is, I think, 2. And instead of using 8, you are going to use 12 inches, and you are going to do the same thing. Longitudinal weld length is 8 inches, so you have to multiply it with 0.85, and for transverse you have to multiply it with 1.5, and to see like which one is controlling. So this one is controlling. So this is the strength of welded connection, okay. And let me add something here if I can. Thank you, I can come here to okay, when we have a welded plate, okay, like this and this, okay, it is connected to another plate with the help of a fillet weld, okay. This fillet weld is here, okay. If you have this type of situation, you don't, in order to evaluate, I forgot the spelling of evaluate, okay. Let me compute the strength of the connection. You don't use 0.85 times longitudinal plus 1.5 the transverse side, okay. But if you have end returns here, this is called end return. Okay, end returns. These are called end returns. End returns. Okay. So why end returns are provided and what is the minimum size of the end return? The minimum size of end return, let me write it here. Size is twice of leg of the fillet weld, and where this leg, this is at least they should be of this length. Okay, this is minimum length. Okay, this is minimum length of end return. Okay, so if you have this type of situation, and why end returns are provided, because when there is a load here, so there will be some stress concentration here. Okay, so if you provide these end returns, the stress concentrations, where is that stress concentrations are reduced by the end returns. Okay. One thing more we want to discuss is that let me, if I remember, if we want to design a welded connection, what is meant by this statement? This statement. Anybody from the class that what is meant by design of welded connection? Make a guess.
The shearing resistance.
Yes,
Line
we
or weld.
want to have the length of the welded connection. Design meant number of bolts required. Length of the weld required. What should be the length of the weld? Okay, how we can do it, how we can get it? For example, do we have another slide? Just give me a moment. Yes. Okay, you can see here that up to here the procedure will be the same. Okay, you will evaluate these three limit states. Okay, and these three limit states, you know, where is that? Yeah, you have three limit states. You have shear strength, of welded connection strength. You have what else you have? You have shear rupture, shear yielding of the base metal. You have shear rupture of the base metal. So you have to select minimum of these three. Okay, and these values will be in kips per inch. Okay, for example, there is a plate here like this, and I want to know the length of the weld. Okay, this is about 10 inches, say. And I did my analysis and I computed these three values, and I will select one value. One means the least value. So what I'm going to do is, if I remember correctly, this is in inches, this is in inches. You have to divide this by this value, and you will get the length. Okay. If you want to have more length, so you will add 10 inches to the other side. If you want to have more length, you can add this dimension as well. Okay. Let's say this is 5. 10, 10, 5. Divide by this value, you will get the length of the weld. So this is what we are going to discuss, and we will discuss this in the coming class. This will be 5 to 10 minutes. Okay. So we will cover this aspect, design of welds. So today we analyze the welds, and in the coming class we will do the design. This procedure will be the same, but you have to just do one additional operation. Okay. Okay. Thank you very much. Any questions?
Okay.
Yes.
No, sir.
I know it was a bit lengthier today as well, but it is not so difficult. Okay, most of the lecture was theoretically based, so there were 2 examples. So go through those examples. Okay, if you have any problem, you can come back to me. Okay, you know my office, so you can write to me that I have a problem. Okay, the things were communicated effectively today in the classroom. Okay.
Yes.
Okay, I will be staying in the classroom up to 10:45. So anybody of you would like to leave the class, so they can leave the class. Okay.